Generally, the topology in and its extension, general topology and its extension. In 1937, Cotton formulated the concepts of filters and ultrafilters, so which were later developed by Robert Schmidt and Grimson as a part of general topology. But these mathematical tools of general topology have been found wanting in the study of various problems and topological nature in areas like a control system, signal processing, logic and computing, and system theory. This is due to the fact that the general topology deals only with the infinite spaces. In 1961, Homer brought various extensions in general topology, such that his theory could be applied to finite sets also. A filter in general, as defined by Homer, is on ordered dichotomy over a set, that is accepted elements, rejected elements. Let us take for instance, a normal algorithm n over an alphabet A. N is a filter in the sense that it divides the free monoid A star into two disjoint sets, one symbol and another symbol. The first symbol is a set of all strings in A star, to which n is a definite, and another symbol is a complement with respect to the A star. So the normal algorithm filter in n is represented by the ordered dichotomy. Following the notion of a general filter, the Tamburan developed the notion of an extended filter, which is a generalization of the concept of a filter due to the pattern. So an extended filter over a finite set is a set which consists only of elements from the power sets of the given set, other than the null set, such that every element present in the filter set ensure the presence of every one of its supersets which are elements in the power set. So example, at x is equal to a, b, c, then its power set is empty set A, singleton A, singleton B, singleton C, pair sets A, B, A, C, B, C, A, B, C. So one can construct a filter set F whose elements satisfy the following property. So any element of F ensures the presence of all its superset present in the power set of X. For example, the set F is equal to a singleton A, B, A, C, A, B, C. So it's a valid topological filter set. Since every element in F ensures the presence of all its supersets, one can construct 18 such topological filters from ground set X, capital X. So an extended filter is called a constructive extended filter. So that means CEF. So when all sets or operations are defined, normal algorithm. So this is shown the filter contents. So filters F1 to F18. Cardinality numbers. So F1 is A, F2 is 6, so and so on. F18 is 1. The lattice is constructed as given below, whose elements are 18 topological filter defined over a ground set X, set A, B, C. Note that the symbol is a partial order relation of subset of the F1 is a supremum and F18 is an infimum. We observe that we transfer the finest supremum to the closest filter infimum. We arrive at the sequence of states called the linear maximal chain of filters. One can enumerate 48 such linear maximal filters, such chain which are given below 1 to 48 maximal linear maximal filter chains. A constructive next constructive Cotton filters. A constructive extended filter is called a constructive cotton filter if it is satisfy an additional condition that the intersection of any two filter elements. So is also a filter element. So let X is equal to ABC. The one can construct 7 cotton filters as shown in the lattice. So lattice, the filters A, AB, AC, ABC, B, AB, BC, ABC, and C, AC, BC, ABC are called universal filters. So let us now consider 3 cotton filters F1, F2, F3 over X0. Then F2 is used to be the interpolate filter of F1 and F3. Only when there is no interpolate filter between F1 and F2 and F2 and F3. So given 2 cotton filters Fi and Fj, later for instance is said to be a just finer filter of the former, just finer filter of the former only when there is a no interpolate filter between Fi and Fj. A constructive cotton filter is defined as an ultra filter if it satisfies the following 3 conditions. One is cardinality of the filter elements, that means subsets must vary from 1 to n, where n is the cardinal number of base set X0. Second condition, one and only one of the filter elements should necessarily be the cardinality 1. Third condition, all those elements of the power set X1 which contain the filter element of cardinality 1 must also be present in the filter set. The specific results concerning constructive cotton filters. So it is not harder to see that any ultra filter Fu over X0 does not have just a finer filter. Similarly, one can see the coarser filter that would be defined over X0. So is CF containing the base set X0 as its only element. A linear filter chain beginning with the coarser filter and ending with the ultra filter is called a maximal length filter chain. A maximum of n ultra filters of the constructive cotton type would be constructed over a given base set X0 of cardinality n. For every such filter, there correspond n-1 factorial, so maximal length filter chains. This implies that for any base set X0 of cardinality n, one can construct a maximal of n factorial. So maximal length filter chain. So given a constructive set X, a constructive power set X1 possesses a relational structure of a complete lattice in which the lower bound of 2 subsets is the intersection and the upper bound is the union. The complete lattice is partially ordered set in which every non-empty subset has a supremum and an infinity. So next theorem, given a constructive base set X, the family of all constructive extended filter over the base set possesses a relational structure of a complete distributive lattice, which is denoted by the symbol. So where contained in is relation is read as a coarser then. Next slide, the quantifiable measures of a constructive extended filters. So Erlandson introduced 3 different measures of the filtering capabilities of the extended filters. First one, the ambiguity of a filter. Second one, the discrimination of a filter. Third one, the resolution of a filter. In addition, he introduced a metric over space of a filter. A measure of how close or far apart 2 different filters are. So significantly, Erlangen measure can be given a constructive interpretation as well. In fact, we would interrupt these measures as normal algorithmic operators, mapping a metric lattice of extended filters over a constructive set into the metric space of a constructive real numbers. But to describe our interpretation, we need to go into the details of constructive mathematical analysis, starting from the formulation of various constructive numbers, functions, and function spaces. This would cause a diversion from the main flow of this presentation. So we describe in what followed the quantifiable measures for CEF on a similar lines of Erlangen without losing the constructive aspects in them. So first one, the ambiguity of CEF process. So psi A is equal to modulus set x such that x contained in Fi and both x and its complement x bar are in Fi divided by 2 power k minus 1. So universal filters are non-ambiguous. The coarser CEF contained in non-empty is the least ambiguous filter and the finest CEF is the most ambiguous filter. Next one, the discrimination of a CEF process. So discrimination of a CEF Fi of k elements is a measure of the number of elements accepted by it. We denote this measure as psi d and define it. Psi d is equal to modulus Fi divided by 2 power k minus 1. The finest CEF is the most discriminating filter and the coarsest CEF is the least discriminating filter. The resolution of a CEF process. The resolution is a measure of the smallest size of the elements accepted by a CEF. So we define this measure in the following manner: let Fi be a CEF and sigma be its base. So now we denote the resolution measure of a CEF Fi of a k elements psi r and define it as psi r is equal to 1 by modulus sigma I. So distance measures, third one is the distance measures between two CEF. So consider two arbitrary CEF, Fi and Fj in a lattice of a CEF. Now between these two CEFs is given by psi del is equal to modulus Fi union Fj minus modulus Fi intersection Fj divided by Fi union Fj. Example, let A be an alphabet and x naught is equal to ABC be a base set. One can construct 18 extended filters over the set x naught. So the complete distributive lattice formed by this 18 CEF is once again shows here along with the distance measure indicated at the appropriate places. So distance measure, so filters F1 to F18, cardinality numbers. Next to the F1 is a supremum, F18 is a minimum. So we find the distance measure psi del from F1 to F2, F1 to F2 is 1 by 7, F1 to F3 1 by 7. Similarly, we find from F17 to F18 is 1 by 2. So combinatorial theorem involving quantifiable measures of CEF, the theorem that x naught be the base set whose coordinate element is k. Then the following statements are valid. One is the finest filter is the most ambiguous filter over x naught. The coarser filter is the least ambiguous filter over x naught. All the universal filters are non-ambiguous filter over x naught. So all the CEF which are coarser than universal filter over x naught whose k less than or equal to 3 are non-ambiguous filter. Fifth one, the ambiguity greets in certain CEF which are coarser than universal filters over x naught whose k greater than 3. Next theorem. So let X naught be the base set whose ordinal number is K, then CEF whose ordinal members are greater than 2 power K minus 1. Do not possess a pairwise interpretation property, that means PIP. Next theorem, the discrimination measure of a family of the CEF over base set X naught of cardinality K, the ranges from 1 by 2 power K minus 1 to 2 power K minus 1 by 2 power K minus 1 in steps of 1 by 2 power K minus 1. Next theorem, for base sets with K greater than or equal to 3, for every universal filter which satisfies both FIP and PIP yields a universal filter of resolution 1 by K, which satisfy only PIP when the base element of the former is replaced by its complement with respect to X naught. Next theorem, given a base set X naught with K greater than or equal to 3 and K being an old number, one can construct a universal filter with the K by 2 elements. So these are all the references. Thank you for attention. Thank you for giving opportunity.